for the graphite, what you are seeing is lead, right? So, so this is actually, if you just look at the history, you can see that from AD 1550s, is a material which is used to be available naturally, right? Especially in graphite mines, right? So from 18th century onwards, people started using it in pencil, right? So that's what we call it as the pencil lead, right? And other than that, it was also used by sailors to lubricate their ropes, right? So still we are also using it for lubricant in different applications, including the brush of electric motors, which is conductor as well as a lubricant, right? So this is not a new material, but you can see that just by modifying this material, you can get a wonder material, right? So today's discussion will be focused on a graphene material, and I will just discuss how the graphene, or what are the properties of graphene, why the graphene is so important, how we can prepare graphene, and what are the current applications or current development in the area of graphene, or graphene science and technology, right? So you can see this is a natural piece of graphite. And you can see that this is just lumps of graphite you can obtain from mines. So it just looks like a lustrous solid block, right? And you can see that the graphene is, by definition, so just before we start, just to give you some definition of this material, right? So if you, the graphene can be defined, graphene is a material which is 1 atom thick. Just remember that, it's just 1 atom thick planar sheet of sp2 bonded carbon atoms, and that are densely packed to form a honeycomb crystal lattice, right? So it's a, it's basically a sp2 bonded carbon atoms. I hope you know the meaning of sp2, that is double bonds are there, right? And you can see the molecular structure of graphene in the left side. So these are just a molecular structure. You can see the double bonds. So you can see, and in the middle, you can see the real image of a high resolution transmission electron microscope of graphene. You can see the hexagonal structure of graphene, and you can see the carbon atoms. So these are the real carbon atoms that we can see by using electron microscope. And the right side, what you are seeing is the scanning tunneling microscope of graphene. So where we can see the carbon atoms, and the scale you can see is 0.5. Okay. So if you just remember that we are actually preparing graphene from graphite, right? So graphite is nothing but our pencil lead. The pencil lead contains some graphite, and just remember, or just it will be something like, if you just consider a book, it has multiple pages, right? So like that, a piece of graphite is like a book. It has a sheet structure, layer structure, right? And if you just peel one sheet from a book, right, just to peel off, just to pull one sheet, you can consider it as a graphene. So graphite is nothing but a assembly of graphene structures. Graphite is formed by the assembly of millions of sheets, millions or billions of sheets. Then you'll get the graphite, right? So our aim is, or our discussion mainly focus on a single sheet. So what is this property of a single sheet? What is amazing about this material, or what is wonder about this material, right? So we consider this as the material which is God's own material, we can say, because it has all properties that we are looking for, right? So only thing is that you have to plan according to your interest, right? So a lot of interesting applications you can find in this material. So this is actually, probably most of you are familiar with these two guys. So this is Jim and Novoslov. They got the Nobel Prize in 2010 in physics. They are from Manchester University. So their contribution was to extract this single atom thick or thin layer of graphene from bulk graphite. Right? So that was their contribution, and they got the Nobel Prize. So they were able to pull out the graphene from the single sheet of they can able to pull out a single sheet of graphene from a bulk graphite material, and they have used a technique called micro-mechanical cleavage. Micro-mechanical cleavage, or we can call it as a Scotch tape method. So simply you just use a Scotch tape or tape, a sticky tape, then just pull multiple times to cleave a single layer of graphene. Right? So that was their contribution, and they are successfully able to do it. So you can see different graphitic forms, and the graphene is actually, we can consider as the mother of all the graphitic forms. So you can see the single sheet of a graphitic form as graphene, and that can be folded to form a graphene or a carbon nanotube, or we can just make it the ball, a zero-dimensional buckyball, a fullerene, right? So different forms you can make from this graphene. So including graphite, that's a 3D structure, graphene is a 2D structure, a nanotube is a 1D structure, a buckyball or a fullerene is a zero-dimensional material, 0D. So different materials you can make from this graphene. So we consider graphene as the mother of all the graphitic forms. Okay. So you can see the different graphitic forms, including the diamond, the graphene, the fullerene, tubes, etc. So these are just standard, some images most of you are familiar with, right? So let us see what is the useful properties, why we can call it as wonder material, a godsend material. And you can see that the properties or what is special about the graphene. So you can see that I just listed few properties of graphene. So you can see that it is have a tensile strength of 130 gigapascal. It's very, very strong material, and you can see the strongest and lightest material on Earth. And you can see it has a Young's modulus of 1 terapascal and having a charge carrying mobility of around 200,000 centimeter per volt second. So we consider the charge carrying mobility as a ballistic conduction. It's very, very fast. It's because ballistic conduction is possible with graphene. And the thermal conductivity, you can see that it is 5,000 watts per Kelvin. So that is almost like 10 times better than copper, and its carrier mobility is 100 times that of silicon. 100 times the carrier mobility is 100 times better than silicon, and it has a transparency of 97.7%. That is that much transparent. The material is that much transparent, right? And has a very high specific surface area. You can see that it has 2,630 meter square per gram. So that is a specific surface area. It's a huge value for this material. So huge surface area, right? So as you know, any material, when the size reduces, the surface area increases, right? So since this material is very, very thin and having few micron or few nanometer size, and a specific surface area is approximately around 2630 meter square per gram, and has a band gap of 0. So they don't have a band gap. So they have very the conduction band and the valence band meet at the Dirac point. So they have a 0 band gap. And there are a lot of research going on to tune the band gap, just introduce some band gap by just doping the material with some other material, right? And if you look at the gas permeability, and you can see that they have nil. They don't have any gas permeability, even the smallest atom, what we call a helium, which is having a diameter of 31 picometer, cannot pass through this membrane, right? So hydrogen or any gas, so the gas permeability is very high, gas impermeability, right? But we can see that water can be penetrated. So that is very interesting phenomenon, and that is used for water purification technology, development of water purification technology. So the water can make a hydrogen bonding with the graphene, by which it can move through the material. So a lot of interesting things you can observe. And as I told you, the current density of this material is almost 100 times that of copper. So it's better than copper. Material is better than copper, better than silicon, better than silver, better than steel. So you can see that if you look at the properties, it has very superior properties than any of the materials, right? So that's why it's called a wonder material, right? Or what we call it as God's own material, right? So a lot of things we can do. So wherever we need such applications, so this material can be a very good candidate, right? So you can see that this is one cartoon shows that a hammock, right? So it's a 1 meter square graphene hammock. So that can support 4 kilogram cat, right? And it has very negligible weight, equivalent to weight of the whisker of the cat. It's around 0.77 milligram, right? But still, you can see that it will be almost transparent, right? So the material is, if we can make a material, a 1 meter square graphene hammock, it can support 4 kilogram cat, but at the same time, it won't be, we cannot see it. We cannot see the hammock because it will be something like an invisible material, right? But at the same time, your cat will be just floating on the air, right? So it's something like that, right? And if you look at the surface area, as I told you, a football court is having a area of around 2,630 meters square, right? Okay, graphene is having a similar surface area. That means you take just 1 gram of material. If you just take 1 gram of graphene, you can spread the entire football court. So if you have a very huge surface area, right? Huge surface area, right? And you can see that, as I told you, we have many other properties. It can be stretched to a quarter of its length, right? And it is stiffer than diamond, and you can see it's very strong because it's a crystalline structure with ultra strong atomic bonds, make very strong material. And as I told you, we have it's 200 times better than silicon with respect to the electricity or the electron mobility. And in different applications, especially for biocompatibility and biomedical applications, they have very biocompatible nature, right? And also you can see that it absorbs only 2.3% of the white light. So it's almost transparent and very strong material, right? So how will you make this material out of the bulk graphite? It's a very simple method. There are different methods are available, basically top-down process or bottom-up approach. So for top-down, you use bulk graphite, then you use micromechanical exfoliation. So like as I told you, Scotch tape peel-off method, just to peel each sheet one by one. So that is a top-down process. And also you can make some colloidal suspensions of graphite oxides, and also you can make graphene. Otherwise, you have to use the bottom-up approach. You start from simple molecules. So that is the meaning of bottom-up approach. So start with the small molecules like methane molecule. Then you can use the chemical vapor deposition technique. Right? So that is a very widely used technique, the CVD technique, because it can do a very thin layer of graphene. Right? But it is a little bit expensive. Right? So you can make graphene either by top-down or bottom-up approach. So this is very simple. What I'm showing you here is a graphite oxide method. So that's very, very commonly used method, and you will get a very good yield. So the method is called modified hummus method. It's just take a graphite powder. You can buy in any shop graphite powder. Then just use some chemicals like a strong oxidizing agents, acids, and permanganates, etc. Then you convert it to a graphite oxide, right? Then you just do some ultrasonation so that you can exfoliate these films. So what you are seeing here is this process involved in preparation of graphite oxide, right? So then you can further do some chemical treatment to change to the graphene, or just to reduce the graphene oxides to the graphene. So that is also possible, right? So depending on your requirement, you can do different modifications on this material. Right? And other than that, as I told you, we can use a CVD process, a catalyst-based graphene production by CVD. So either you can use copper or ruthenium or rhodium or nickel catalyst. Commonly used catalyst is copper. Copper can easily be used as a catalyst, right? And even you can buy graphene deposited on copper. Strips are available in the market. You can just buy it. So copper will be there. Only thing is that you have to etch the copper away when you want to use the graphene, right? So commonly used, very commonly used catalyst is copper, right? And you can see this is this typical CVD process. What you are seeing is the CVD process. So the precursor is methane. You should have a carrier gases like hydrogen as well as inert gas like argon. And you have a simple quartz furnace. You can see just a quartz tube contains your well cleaned, well treated copper foil, right? And just control the fluoride of the gases, and then you have heat at 900 degrees centigrade, right? So the methane will decompose and it will form a thin coating on this copper surface. And so you get the graphene, a single layer, monolayer graphene you can get without much defect on the surface, right? So they will have very high conductivity. Usually CVD graphenes are of high quality, right? And if you want to transfer this graphene, you have to do some steps. For example, after the CVD process, you can just spin coat some methacrylate PMMA solution on to this copper graphene piece. Then you just dry it, followed by you can just etch away the copper. So the graphene will be on the PMMA sheet. Then you can just transfer it to any substrate just by dissolving the PMMA using some solvents like acetone, right? So you can transfer the graphene to wherever you require. So that's a very simple process. So what you are seeing, this is just optically microscope, the image of a monolayer as well as a bilayer graphene. So these are actually reflecting images from the microscope. These are actually exfoliated graphene layers, right? So this is the TEM, transmission electron microscopy image, graphene flakes. So you can see that very thin sheet-like structure you can see. So this is a graphene sheet, right? So the scale is around 100 nanometers, right? And this is the, here also you can see the high resolution image, TEM image, where you can see the lattice, because lattice is carbon atoms, the highly ordered structure you can see in this image, right? So this is just overall scanning electron microscopy image. You can see the graphene flakes, right? So when you do some chemical synthesis using modified Hermann's method, most of the cases you will end up with a graphene oxide having a morphology. What are you seeing here, right? So usually the graphene is characterized using Raman spectroscopy. So we can use either Raman spectroscopy or any electron microscopy technique to characterize the graphene. So usually commonly used technique is Raman spectroscopy. So usually, so you can see that the if graphene is formed, you can expect the G band is the G prime band, and you can see the 2D band, etc. So depending on your quality of the graphene, you can see the ratio. For example, if you have the 2D band to the G band ratio, if it is around 0.84, you will have the few layer graphene, and if it is around 0.44, we consider as the multi-layer graphene, right? So the Raman is commonly used technique for characterizing graphene material, right? So if you just look at the, so that's all about the preparation of the graphene. So the properties, the preparation. So let's see some of the interesting applications. You can see graphene applications. You can see the n number of applications you can find. So you can see that either you can use a single or multi-layer graphene, or you can use bulk graphene or single layer graphene. So application is divided into three. Three colors represent three different materials: single layer, multi-layer, bulk, as well as single layer. You can see it starts from batteries to supercapacitors, plastics to polymers, structural materials, additives for 3D printing, automotives, thermal management systems, rubber and synthetic applications as fillers, lubricants, concrete and cement, magnets, sensors, electronics, semiconductors, water filtration, transparent conductive electrodes, optoelectronics, transistors, pressure sensors, touch screens, photodetectors, spintronics, NEMS, Hall effect sensors, barriers, films, and coatings, conductive inks, aerospace, energy generation, corrosion resistance, medical applications, waterproofing, plasmonics, quantum dot composites, piezoelectric transducers or sound transducers, sonics. So you can see that a lot of interesting applications you can find from this material, right? So this is very interesting. That's why as I told you, this is a wonder material, right? So we will just look in few interesting applications. One is graphene in flexible displays. So what you are seeing is some flexible displays where mobile phone can be flexed like this, wrapped like this, bent like this, right? So usually the role of this graphene is to substitute the currently used transparent conductive electrode, which is nothing but indium tin oxide. So most of your display devices, including mobile phones, laptops, or televisions, we use indium tin oxide electrodes, right? And the problem is that indium, we don't have much indium on the earth crust. So there is a scarcity of indium, and indium is also very expensive, right? So the idea is to replace this TCO, or transparent conductive electrode, indium tin oxide, with the graphene, right? So that is the idea. So which will make, because this ITO is a brittle material, so you cannot bend beyond an angle, which will form cracks on the material. So we cannot use indium tin oxide if you want to use a real flexible display. So the best material you can think is the graphene. So graphene can, because graphene is highly flexible material, it can do n number of flexing. It's very strong material. So there is no issue with any crack formation, or because this is basically an electrode. So electrode should be intact, even multiple bending, right? So that is the substitute for indium in display applications that can be used in organic LED display, LED based displays, or in LCD based liquid crystal based display. Anything you can use. So what you are seeing is the graphene modification of our current LCD screens, LCD televisions. You can see the graphene is used. You can see the red colored, it is highlighted in red color, and that is the graphene films. That is nothing but the graphene electrode. So you have, if you look at the cross section of your display, so it will look like this. So the liquid crystal is sandwiched between two electrodes, right? So the top electrode and bottom electrode, and so these two electrodes can be, currently we are using ITO, indium tin oxide, but you can use graphene. So that will be a revolutionized technique. So, and especially since the graphene is having very good optical transparency, so it can give better image, right? So that is where one interesting area we can think about. Then moreover, you can think about graphene in OLEDs, organic light and diodes, which uses, you can see here the graphene called a substrate can act on the electrode, right? So in this case, we are basically using the electrical conductivity of graphene, and also we are looking at the transparency of graphene. So transparency as well as the electrical conductivity of this material is used to make this type of OLEDs or display devices, because we need transparency as well as the electrical conductivity. So that's why we are going behind such flexible OLEDs based on graphenes. And you can see on also for touch screens we can use capacitive touch screens or other type of resistive touch screen. You can use either this graphene based electrodes. So this is one example of a touch screen which uses graphene, right? And also for so told you graphene for flexible thin film displays like this. We can see this is a graphene based OLED thin film display. So that is used for making bendable or flexible mobile phones, or flexible display, or some particular applications, right? So that's one area, and that is the information display. Information display area, we can use graphene as electrode as well as the transparent material. Then even for solar cells, we can also think about ITO replacement. So wherever ITO is currently used, graphene will be the best candidate, right? So you can see this organic solar cell. This is just like a PN junction. You can see the you have two electrodes, one electrode 1, electrode 2, electrode 1, where the sunlight is coming in, where we can use graphene as electrode. The other side, you have the aluminum. You can use either aluminum or calcium electrode on the other side. But the electrode which is facing the sun should be graphene, because it should be transparent as well as electrically conductive. So this is just a very good replacement for ITO. So a lot of future will be there in this type of development of this type of display or solar cells, right? And for sensors, so sensors also, if you look at sensors, graphene is one of the widely used material for developing sensors. So what you are seeing is a platform electrically detect DNA molecules using some electric field. So you can see that. So this can be used for sensing different molecules. For example, graphene sensors to detect a single molecule detection, single molecule. So that's very difficult in normal cases, single molecule detection. For example, air pollution. If you want to see the air pollution, we can detect the presence of carbon dioxide or carbon monoxide, or if you can also detect the presence of volatile organic gas molecules, VOCs. VOCs are actually making a lot of health issues because it contains in most of the materials we use in our house. For example, furniture, household goods, homes, offices, schools, car, etc. A lot of VOCs are there. Volatile organic compounds are there. So that is polluting our atmosphere. So this can be used as a detector, a sensor to detect single molecules, right? Or even for explosive detection, we can use graphene because the explosives will have a very low vapor pressure. So the molecule will not come out. Maybe a few molecules will be coming out. And so if we use graphene as electrode, it can sense the single molecules, right? Any of the explosives you can detect. So basically, we are making use of the high electrical conductivity of graphene, and we have a high carrier mobility as well as large surface area, right? So that's, and also we have very high ultra sensitivity of this material to the analytes, so which will make graphene a very good sensing element or a sensing platform, right? And you can see this is just for a gas sensor for ammonia sensors or hydrogen sulfide sensors in mines and all. We can use, these are all based on graphene, right? So one interesting thing I would like to discuss today is the you can see here the graphene biosensor.
So please share screen. Share screen has gone.
What you are seeing here is the the sensing of the COVID-19 antigen. So you can see this. So we are basically, you can see that the COVID-19 patient, and you can take the antigen from this using a swab. And so basically what we are doing is we are making a field effect transistor. So this is a FET sensor, field effect transistor based sensor. And you can see that a graphene is here. So the graphene is actually here between the source and the drain, and this is your gate. And you can see that the using because we cannot simply attach the SARS-CoV-2 spike antibody with the graphene. So we need a linking molecule. So what we are using a linking molecule in this case is, you can see that this is a chemical compound that's called 1-pyrene butyric acid N-hydroxysuccinimide ester. So this is actually acting as a linking probe linker, right? So you can see here in this picture, so here you can see in this picture, you can see this is your graphene and this is your FET. This is the source and drain, and graphene is deposited here, right? And this is your linker, and this is your antibody, the spike antibody. So this is the antibody from the spike, and this is your virus. And so there is antibody antigen interaction at this point, right? So basically that is the mechanism what they are proposing. This is a recent paper published last month, and then you see Kim and et al. This is from American Chemical Society, ACS Nano. So you can just refer this very interesting article. So this is just published in a week time because of the emergency requirement of such sensors to develop to meet this pandemic, right? So you can see this is basically what we do. So the as I told you, the linking molecule is this PCBC, that is a pyrene butyrate N-hydroxysuccinamide ester, right? So that will be acting as a linker. So basically what we do is that the process is something like what I discussed earlier, and you will be making a transistor from using the graphene, and because graphene has to be transferred from a copper foil, because when you purchase graphene, graphene can be purchased as a CVD graphene on a copper foil. So the copper has to be removed, then it has to be transferred to the PMMA, then you just remove the PMMA using acetone, then slowly you transfer to the FET, right? Then you will have the treatment with this linker, then you have the antibody, then you have the real molecule, right? So what you are seeing is some of their result. I just thought that this will be very interesting for the current situation. And you can see this some of their result from this group, right? So you can see that this is the surface analysis of the pristine P base. So there is nothing but the linking molecule, the succinic acid ester molecule, and so this is your source and drain. This is your source and drain, and this is the graphene is here. The graphene is here, right? So this is, and you have the electrodes coming out, and you can see here the some of their characterization they did for this material. So you can see that this is just Raman spectroscopy. So they want to know whether graphene is there and what happens to the graphene when they link with this P base, right? So P base is nothing but the linking molecule and the pyrene based linking molecule, and you can see this. So the G band, the 2D band corresponds to the graphene is also visible in the Raman spectrum, and you can see that some changes in the spectrum because of the presence of the P base which is attached to the graphene. So the change in the spectrum is due to the presence of P base in the surface of the graphene, right? And that is also visible in this picture. So they have just calculated the they have this the Raman imaging. Raman imaging also they have done. So that's what they are showing this in DNE. Right? DNE is a Raman image, basically showing the presence of the P base graphene. So this is the graphene pure graphene, and this is the P base graphene. So you can see the color change that corresponds to some differences in the interaction with the laser light. So that is basically they are confirming the bonding of the P base with the graphene molecule. They are further confirmed it with X-ray spectroscopy, the X-ray photoelectron spectroscopy. You can see the XPS peaks. So this actually, this is for the graphene, and this is for the P base. Basically, they are looking at the nitrogen peak. So they can see this is the nitrogen 1s peak. This is the zoomed XPS spectrum of this P base graphene. So you can see that the nitrogen 1s peak is present, that showing that there is a bonding between graphene and the P base. And further, this is confirmed here. So you can see that the presence of these bonds, carbon double bond, carbon O bond, especially the CN bond, are etc., showing the presence of the substitution or doping of the P base with the graphene. So this is the atomic force microscopy image. Here also they are just basically looking at the roughness parameters. So you can just the root mean square roughness is 0.96 for graphene. After doping with a P base, you can see that it became 1.5, basically showing the presence of those molecules on the surface. And you can see the white spot maybe representing the increased height due to this material, right? And they have also tested the sensitivity of the COVID antigen protein. Basically, they are detecting the antigen protein, right? So you can see that. So this is a transistor FET-based sensing mechanism, and you can see that these are just some of their results. They are able to detect LOD, the lower limit detection limit is around 1 femtogram per ml. So that much sensitivity they are claiming, right? And this is just a normalized response with concentration. So the linear response shows that there is a score for this type of devices, and they are even able to distinguish between MERS-CoV and SARS-CoV. So that is also they are able to detect the response. Basically, they are looking at the drain source voltage. So what is variation in drain source voltage with the presence of this antigen interactions. So this is also the normalized concentration. So they are also getting a linear response. So that is actually telling that. So this will be one of the maybe future sensor for COVID-19, because I think this what I understood is that this will take less than a minute to detect the presence of the COVID antigen, and also there's the spike protein, and also we can see that the sensitivity is very high. So in the initial stage of the COVID infection, the presence of that protein can be detected. So the sensitivity is very high and very fast. Maybe this may be one of the future sensor for this type of pandemic. Right? Then other than that, if you just look at the composite side, graphene-based composites are also very interesting area. And you can see one example is why we are going with graphene-based nanocomposites, right? Whether it can replace the copper. So that is also a question to be asked. So you can see that why we are going behind a nanocomposite based on graphene. So you can see that a Delta rocket can lift around 23,000 kilograms for about $400 million, right? So that means if you calculate, if you want to take 1 liter of water to space, the approximate cost would be around 12 lakhs rupees. So it's a huge amount, right? So the idea is to reduce the weight, right? So for example, copper is having a density of 8.96 gram per centimeter cube, whereas the graphene is only 1.5 gram per centimeter cube. So there's a huge difference in density. For example, if you take a Boeing 747 jet plane, it contains 2 tons of copper wires, 2 tons. And if you can replace copper wires with graphene-based wires, so you can save a lot of weight. So weight is nothing but money, right? So such type of interesting application you can find in spacecraft and aircraft structures. And also we can, basically graphene can have very high strength. So if you make composites from graphene, we can make very strong composite structures without affecting any of its dimensions, right? We can save a lot of weight, right? So that way it will become more efficient, right? Even in sports, you can see this type of graphene-based nanocomposites based tennis rackets or squash rackets. It's available in the market nowadays. It's basically graphene-based nanocomposites, right? So that's also available. So I just show you some of what we are doing in composites here in our laboratory. You can see these are just some of the different graphitic forms we have synthesized. So you can see this is graphite flakes. So this is graphene sheets. So this is exfoliated graphene sheets. You can see this exfoliation or widening of graphene sheets, right? So this structure, this morphology, basically telling you that there is exfoliation or the layers are separated. That's why we are getting this type of structures. So as you can see, this is a crumbled graphene sheets, and this is highly wrinkled graphene sheets. So different graphitic forms we can simply synthesize in laboratories using any chemical methods. So these are just some of the composites we are making. We are making epoxy-based composites for different applications. So just the process is very simple. Just mix epoxy with the graphene material, then you can just mold it to the solid form. Then we do testing for example, we are just measuring the nanocomposites for flexural strength. So you can see that there is increase in flexural strength. You can see the flexural strength is increased, 10% increase if you use reduced exfoliated graphene, right? And if you use exfoliated graphene oxide, they have another 10% improvement in flexural strength. And for example, other composites is also made. This is actually for composite strength measurements. This is for composite strength. Here also we are getting around 15 to 10% improvement. So basically what I am trying to tell you is that we can make composites using graphene or graphene derivatives that can increase its mechanical properties. So it can improve the mechanical properties of your material, right? So this is just showing the fracture surface after adding exfoliated graphene oxides to the epoxies. So what you are seeing is just fracture surfaces. So this is actually your exfoliated graphene oxides on epoxy resin. So this is epoxy resin, and you can see this is agglomerate particles, right? Then we can also think about different composite fabrication process like hand layer process. So what you are seeing is a setup for molding composite material. So this is called vacuum bagging technique, right? So basically what we are doing is we are basically making fiber reinforced composites using graphene oxide. So the composites contains some resin, it contains some graphene. Along with that, you have some fibers, for example, glass fibers or carbon fibers. So I'm just showing you some of the interesting results. You can see that the flexural strength and flexural modulus, you can see there is considerable increase. If it's just an average, you are getting around 10 to 20% improvement when you add very small about 0.25 or 0.5% of graphene compounds. So basically, what I'm trying to tell you is that we can improve the mechanical properties of any material by adding graphene, right? So depending on your requirement, even for improving, you can see that this is the interlaminar shear strength studies. Here also you can see that there is increase in the by adding graphene oxide, we could able to make a better composite. You can see 30% improvement, 70% improvement. So that much improvement you can find by adding the graphene. Right. So this is another interesting thing. This is called mode 1 fracture studies. Basically, one of the issues with composite material is that their out of plane strength is very poor. That means there are chances that the laminates, so the composites actually are made as laminates. So there is a chance of delamination. So the bonding between the laminates is very poor. So in these studies, what we are doing is we are trying to improve the bonding between the laminates. So that is just showing you this animation based on mode 1 fracture. So we are just peeling the laminates and just looking at the strength. So this is using UTM. We are just doing this testing, and I'm just showing you some of the result using this testing. And you can see that there is even 77% improvement in the mode 1 fracture studies. 77%. So that's a very interesting result when we start using this reduced exfoliated graphene oxide. We have used only 0.5%. A very small quantity of graphene will improve considerably the mechanical properties of composites. So this is what we are seeing with the fracture surface of this composite material. Right, as you can see, this is just the fibers on the surface. We have the graphene materials. Right, and for mode 2, so mode 2 fracture studies also we did using this graphene. So mode 2, basically what we are seeing is a composite material, and you can see that we are applying a force using a 3-point bending mode. And here also we have basically looking at the delamination of this laminate structure. So in this case, we look at the result. Here also we can see that we have a maximum of 54% improvement in the mode 2 fracture studies. So that is using, here also we have used reduced exfoliated graphene oxide around 0.25%. So only a small addition of this material will improve the fracture properties of this composite materials. So what we are seeing this FE some images of the nanofillers, dispersion of graphene oxide on the epoxy materials, so that can be measured using a scanning electron microscopy. And this is also the just mode 2 test specimen fracture surfaces. So where we can see these are the continuous fibers on which you have the graphene oxide percent. And moreover, graphene can be grafted to fillers. So that is also possible. Graphene can be grafted onto fibers using this electrophoretic deposition. So that's what we are seeing. You can see this is a carbon fiber on which we are depositing graphene. Graphene is deposited on carbon fiber, and we have made composites made out of that. So this is what you are seeing. You can see that this is your carbon fiber. On that you have graphene. This is your graphene flakes. You can see that. This is the unmodified graphene fabric, and you can see this carbon fabric, and you can see the carbon fabric is decorated or deposited by the graphene flakes, right? So then you make composites using this electrophoretic deposited carbon fiber. Then you do epoxy and other things. You can just so you have a considerable increase. You can see that around 30% improvement in most of these studies, properties, especially the fluxural studies, right? And also for mode 1, and also we have a considerable increase, around 15% improvement in mode 1. And this is some of the mode 1 test fracture surface studies. You can see the specimens with carbon fibers, right? So on that you have the epoxies and matrix to the carbon fiber. In between you have the graphene is also present, right? Then the thermal properties, which is graphene. Then if you look at the thermal properties, you can see that, as I told you, thermal properties are very important, very interesting thing to see. As I told you, the thermal conductivity of graphene is around 5300. So it's almost 10 times better than silver or copper, right? So thermal conductivity of graphene is also very important, because it is have a ballistic thermal conductivity. It can very fast. I mean, the heat can be conducted very fast, very quickly. So that's why it's called ballistic thermal conductivity, right? So this is one of the product which is based on the graphene material. So basically, it is a jacket used for in cold countries. The idea is that the distribution of heat will be uniform if you wear this jacket. Suppose if you wear this jacket, you will be more comfortable. You will
Hello.
Sir, not audible. Are you speaking? Not audible.
I think now the slides are visible.
Yes, now it is fine.
Yeah, thank you. Then other than that, graphene can be used for tire industry. Tire industry, graphene can be used especially for improving electrical conductivity, thermal conductivity, gas impermeability, low rolling resistance without losing grip, mechanical strength, especially for lighter tires, right? So one of the basic issue with tires is that the tire noise, especially in developed countries. Tire noise is one of the very big issue, right? Tire noise. So the one idea is to use silica fillers instead of usually we use carbon black in tires as a filler. That's why the tires are black, right? But you can think about if you want to reduce the rolling resistance, you can go for silica. Silica is white, so the tires should look white. But the problem is that when you add silica, silica is the insulator, right? So the electrical conductivity will be very poor, right? To reduce or to improve the electrical conductivity, you can use graphene. graphene can be added to the tires, silica tires, to improve the electrical conductivity, because tire is supposed to have some should have some electrical conductivity, especially to discharge any static charge or anything related to the development of electrical accumulation on the surface of the ball, on the surface of the vehicle, right? So the tire should have a minimum electrical conductivity. So by reducing the rolling resistance and also reducing the tire noise using silica, you can improve the electrical conductivity by adding graphene, right? So that's one interesting thing with respect to tires. So different industries use different type of approach. So this is one example of a graphene tire. So tires containing graphene, right? And moreover, one interesting thing is graphene we can use for water filtration, right? So especially for separation of salt from water, salt water separation. As I told you, only water is the only molecule which can pass through graphene. So the mechanism is based on the hydrogen bond, right? So you can see that this is what we do. So the water molecule, you can see the red and white color. That's water molecule, and you can see the sodium and chlorine. So the desalination of seawater. So graphene can be used as a membrane to desalinate the seawater. So you can separate salt from this water, right? So that is also very interesting. Look, then another thing, see energy generation from graphene-based composite material. So this is some of the work we are doing in our laboratory. So you can see that this is a polymer hybrid nanocomposite for energy harvesting. So basically what we are doing is we are harvesting waste energy in the form of a reusable, in the reusable form. So we are looking at the small vibrations, any movements of very small frequency that can be converted to a useful form of energy, right? Any vibration, even human motion, or when you exhale or inhale, even heartbeat, or even some mechanical vibrations because of some engine part, that can be converted to useful form of energy. Especially that's what we call the nano energy harvesting or micro energy harvesting. But the voltage form voltage current produced is very less, but that is sufficient for functioning of some sensors, right? Basically, that's what we are focusing. So in this case, what we are doing is we can just making composites made out of exfoliated graphene oxide. You can see that EGO is used as the exfoliated graphene oxide, and we are actually adding some materials like zinc oxide, some polymers. Basically, we are looking at the triboelectricity that is nothing but static charge, along with the piezoelectricity. So basically, we are converting the piezo or the pressure or the piezoelectric energy, right? So we are just converting the mechanical energy to the electrical energy. So this type of hybrid nanocomposites can be used. So this is one. What are you seeing? This picture is the fabrication of such nanocomposite material or harvesting energy. So the materials used here is EGO, zinc oxide, and PVDF TRFE. That's polymeric material, right? Then we are making a composite out of this, and this composite can have capability to convert energy, mechanical energy to electrical energy, and is also very flexible, unlike any ceramic materials, right? So you can see some devices fabricated here. So this is your composite material. On both sides you have the copper electrode, and so finally you can see the lead wires out, and so the device will look like this. So bottom electrode, top electrode, in between a graphene containing composite material, a hybrid composite material. So when you push or tap on this material, you can see that when you connect it to oscilloscope, you can measure the this is just a finger, human finger tapping, energy from a finger tapping, right? So you can see the voltage developed. It's coming around a small voltage, 1.5 or 2 volt. You can generate this from this type of devices, right? So you can see that this is just an output voltage and current comparison of energy generating devices. You can see that EGO-based material can have a 2 volt with a current of current is very small, but that can be improved further. Usually, if human finger tapping, the force input contact force will be around 267 millinewton. So that much force can generate this much voltage. So further, we have also improved by changing the material to higher voltage also. So that is also another interesting area. So that is called the nano energy generation. polymer nano energy generation. So that is basically using nanocomposites with the piezoelectricity or triboelectricity properties, right? So this is also some other result what we are seeing. You can see this. We are just the previous result was based on the human finger tapping, but this is actually a mechanized tapping. You can see that we have a mechanism to do some tapping. So this, I can see RPM, rotation per minute, 230 to 240. Basically, you can see we are applying more force, and you can see the voltage has raised around 20 to 25 volt. So that is what we get from this type of studies, right? So to conclude our discussion, there are some challenges with respect to the graphene technology. One of the major challenges will be the production volume, right? And the cost is also very high. And another issue will be resistance with current technologies. But nowadays we are looking at silicon-based technologies. If you want to replace with graphene-based technologies, so a lot of investment may be required. And also there are some health and safety issues also involved in this material. So most important challenge will be the price. So nowadays it's a bit expensive, especially when we do for single layer graphene using the CVD process. It is very expensive, right? But in near future maybe that will be changed to more economical, right? So with this, I think I'll conclude. So once again, before I conclude, once again I thank the management, the department for inviting me to on stock on this quantum material. Thank you.
Thank you, sir. So now the session is open for discussion. Questions can be typed on the chat box. Sir, shall I read the question?
Yeah, please.
Can we coat graphene with metal or polymer composite surface?
Can you repeat?
Can we coat graphene on metal or polymer composite surface?
Can you coat the graphene?
Yeah,
the idea is that, for example, as I told you, when you synthesize the graphene using CVD technique, usually the graphene is coated on copper. So copper, if you want to coat it in a copper, is very simple, right? But there are other techniques also. Suppose you want to do a corrosive protective coating, right, for a metal, for example, iron, right? In that case, we can also deposit graphene on iron, so that will protect your material from corrosion, right? So that is possible. And polymers, that can be done, as I told you. If you want to do, you can just transfer this CVD graphene to any polymer surface. If suppose you want to transfer into a polyethylene terephthalate PET sheet, that can be easily transferred just by transferring from copper PET. You can copper graphene. You just deposit PMMA solution, spin coated PMMA solution. Then you etch out the copper. Now you have the graphene PMMA sheet. Now you can just transfer that to the PET sheet, right? So just to dissolve it in acetone, then you can transfer it to a PET sheet. So that way we can transfer to polymer surface also, right? So that's possible.
Next question is from Himanshi Nikhara. Graphene sieve is already proposed for filtering seawater. Shed a light on this also.
Yeah, basically, as I told you, there's a there are research going on for the desalination of water, right? As I told you, graphene can act as a filter also, right? The graphene is the only material, or the water is the only material that is that can be passed through the graphene. So the basic mechanism is something to do with the hydrogen bonding. So that is possible for the desalination. But the difficult, but challenges with the desalination is how to make a nice membrane, because it's not that easy to make a freestanding graphene single sheet as a membrane to pass water. So practical difficulties are there. Probably you may have to use some composite material in which graphene is one of the ingredient, right? So freestanding graphene will be difficult, but you have to find out some support because graphene cannot withstand the hydrostatic pressure. So it should have some support, right? So either in the form of composite or some other method you have to find out. Other than that, theoretically now it's possible. Some research is also going on in that area. You can find in elsewhere in the literature. Yeah. Thank you.
Thank you, sir. Next question is from Faisal C. Does graphene have any role with aluminium 7075 as composites?
Aluminium 7075. You want to make a composite? Can you read it out once again the question?
Does graphene have any role with aluminium 7075 as composites?
Yeah, I think you can add graphene to many of the metals, so that is possible, because currently we are involved in adding graphene to copper, because in the discussion I told you, graphene is almost 100 times more electrical conductivity than copper. So we are actually adding graphene to copper, right? So improve the electrical conductivity so that the I square R loss can be reduced. The heat produced in electric motors, especially for electric vehicles, you can reduce the heat generation. Right? So that is around 35% of the total electrical loss. That can be reduced by improving the electrical conductivity, just reducing the resistance of copper. So like that, in different applications, for example, aluminium also we can add a graphene. We have did that type of work also, but we can add only up to a certain percentage. Right? The problem is that if you add more graphene, what we have found is that the metallic nature, right, the drawability of the material will be lost. The material will become brittle. So maximum 1% is actually advised. So, but you can play with the material. So definitely it is possible.
Thank you, sir. Next question, one more question from Himanshi Nikhara. How and where graphene can be used in building industry? And can it be used as a reinforcing material?
I think building industry, graphene can be used as a reinforcing. So that's what I understood, because there are work going on cement with the graphene. They have added this graphene to the cement, right? So basically they want to improve the compressive strength of the material, right? Overall bonding between the steel with the cement, such type of, and also the bonding between the aggregates. So those are actually, there are literature on such studies. So it's possible to make composites of cement using graphene with the improved properties, definitely. Yeah. But the cost will be high. So that will be one of the challenges.
Next question, sir. If we coat graphene in the inside surface of small tubes, will it reduce water clogging?
Small tubes means what?
It's question from Sijo Matthew. Can you please raise the doubt? Mr. Sijo Matthew.
Hello.
Yeah.
Hello, sir.
Yeah, please.
Sir, in small water transmission tubes, very small tubes, if you coat...
what is the diameter you are talking about?
Sir, very small, maybe 1 millimeter like that.
Okay.
Can you avoid water clogging problem by coating this graphene?
Yeah, there are some papers on that also. For example, graphene is supposed to be hydrophobic in nature, right?
Yes,
so there are chances that So if we can, and also we can change the graphene surface to hydrophilic also, right? So there are some papers where they have a changed surface from hydrophobic like that, so that water will be moved from one end to the other end just because of the polarity differences. So such type of work are there.
Thank you.
One more question, sir, from Dr. Bobby Matthew. Sir, is there any studies conducted on any side effects of graphene on living organism?
I think, yeah, definitely there are studies on health issues related to graphene. Since most of the nanomaterials are has health hazard, graphene, you can also expect some health hazard, especially to compare with the CNT and graphene. I would say CNT is more dangerous than graphene. Graphene, we are using pencils from childhood onwards, right? So graphene we are using a lot I mean, as pencil lead also. But percentage of graphite may be less in pencil lead because Russell thing will play. But still, we are using it. So as of now, I don't think much health issues are not reported. But at the same time, as a nanomaterial, as a nano powder that can go into your lungs, that can make some health issues. Other than that, I haven't read any issues with skin allergy or something like that. It's very common use material. But health hazard may be related to this, especially a small size, especially when we inhale. Okay.
Yes, sir. Thank you. Next question from Mr. Nishant. Sir, compared to graphene, how MXenes will differ? Scenes will differ.
Sorry, can you repeat?
Compared to graphene, how MXenes will differ? Mr. Nishant, can you please raise the question? Okay, sir, next question. The importance of graphene in industrial revolution.
Yeah, that's what we have discussed so far, right? So you can think about all industries, including display, automobile, all industries you can use this material.
So thank you, sir, for your wonderful session on graphene, a wonder material. It was very much informative. You gave us an insight on advances in graphene science and its application. As it is known, science, she is the mother of technology. Thank you very much, sir. I welcome Dr. Julin, Associate Professor, Department of S&H Department, to deliver the vote of thanks.
Respected Soney sir, Principal Dr. Sangeeta ma'am, and all national and international participants, it is my privilege to have been asked to propose a vote of thanks on this equation. I must mention our deep sense of appreciation for Dr. Soney Varghese for his speech on graphene, a wonder material. It was a great effort, and through the speech, we could understand the basics of current research in graphene. Further, we are grateful to our management and Principal Dr. Sangeeta ma'am for the perfect logistic support and guidance extended to this event. I thank all national and international participants for participating in this event. I also extend my thanks to Dr. Milini ma'am for coordinating this event and all our S&H faculty for their enormous cooperation in the organization of this event.